I think we're going to get started. So this is Jake from QUAY is going to talk about service authentication.
So I lost my voice yesterday. So I'm really sorry for what's about to happen to your ears, but bear with me. So as Ed mentioned, I'm Jake. I'm the head of the QUAY project here at CoreOS. And I want to talk to you about service-to-service auth, why you need it, what it is, how you can achieve it, and where we're going next. Of course, this isn't going to work. Here we go. All right, so the first thing I want to impart is the idea that you need to even secure your services. So how many of you guys have a service-oriented architecture where everything in the back end is just unsecured because you trust your network? Okay, it's not unreasonable. But what we really want to do is we want to decouple the idea that access to a service is equivalent to auth. In order to kind of impart this idea, I've got a money service. The money service just has a single method, and the method is, transfer money. Right? So it could be transfer money from my account to somebody else's account, or it could be transfer money from the Fed to my account, whatever. Because we're a microservice-based shop, our services have a really small surface. So we've got another service that just checks if you've got enough money before you transfer it, right? And then you're fronting this whole system to the outside world through an API. The dotted red line is your firewall. So these things are behind your firewall, so you don't need auth. But what if through programming error, the person who writes the API accidentally skips the enough service and goes straight to the transfer service? Now you've got a broken system, right? We're transferring money that we may not even have. Or what if there's a black hat that got in your network and implements the plot of Superman 3 and skims a little bit of money off of every single transfer before it happens? This isn't ideal, and you want to prevent that by locking down your services if you can. And finally, you may have clients that are communicating with your service over the wide open internet. And obviously these need to be secured for, you don't want somebody to be able to pretend to be an ATM and just steal all the money. So this is where this comes into play for our product, QUAY. So we've got a number of different services that can authenticate with QUAY. QUAY Enterprise is our behind the firewall edition of QUAY. And our customers sometimes deploy it in a really wacky fashion. So for example, sometimes they will expose the whole thing to the internet and say, we want our builders to run on a completely different cloud provider. That's Bob up in the corner. So we want our builders to operate on a completely different cloud provider and to be able to authenticate with QUAY and to be able to communicate as if this was service-to-service auth on our network. The thing that initially made us seek out this solution was the idea that we need to bring Claire, which is our security scanner, to parity with QUAY.io, our hosted solution, when we put it on-prem. So on the hosted solution, we just use TLS client certs, and we call it a day. In the on-prem solution, it doesn't always work because of these wacky configurations. All right, so this is just us bringing it up to parity. So we decided that there were a couple goals that we were trying to achieve. So we really want the security to be painless. What we're competing with is no security at all, right? We're competing with the idea, if I trust my network, if I just put it behind the firewall, everything's safe. So we need it to be almost as easy to deploy as that. Of course, security is like the antithesis to painlessness, so really all we're trying to do is make it less painful. And what we've chosen, or the architecture that we've chosen, are smart proxies. You might be wondering why we chose to build our security as a smart proxy instead of a variety of other methods to achieve the same thing. So by actually building it as a proxy architecture was one of the easiest choices we made. So building it as a proxy gives us language independence, which means that we don't really care what the services are implemented in. We're just going to put something in front of the services and in front of the outgoing HTTP requests on the other services. We get great support. Most HTTP clients will respect the HTTP proxy environment variable and just use that to send outgoing requests. And we wanted a solution that gave us non-invasive protection. So as I mentioned originally, the the goal was to be able to communicate between QUAY and Claire. And Claire is an open source project. And we really didn't want to go and have to hack in a bunch of auth and a bunch of QUAY-specific protection into this open source project. So we wanted to be able to protect a service without the service necessarily being complicit in that idea. We were really inspired by the OAuth proxy project for this. If you're familiar with OAuth proxy, you can basically just secure any service by throwing it behind a proxy that will authenticate using an OAuth provider. In our case, we use Google Apps. Of course, there's a few downsides to choosing a proxy architecture. We have to take an extra network hop. We could avoid this if we did all the authentication directly within the service itself. And finally, if we need to communicate over SSL, we actually have to man in the middle of that SSL in order to layer auth on top of that. Okay. And then so we also had to choose a method of authenticating within these actual requests that are being created by the proxy and terminated by the proxy on the receiving side. And by the way, if the proxy stuff doesn't make sense, I'll show a demo in a little bit in an architecture diagram. So the first thing we considered was just using API keys. So how many of you have interacted with a service that uses just statically pre-shared secret of an API key? It's really easy to understand. I just have this secret and I put it in a config somewhere and then everything just works. The hard part about it is actually bootstrapping this whole system. So who wants to generate a key for any one of 100 different services that we're running? And then if you try and share that thing automatically, and if you try and generate it automatically, we now have the problem of securing the secret store itself, right? Like how do I tell the secret store that I am this service that I'm claiming to be and use that to achieve my secret programmatically? We also had some AWS customers who weren't using VPC. Amazon has very few guarantees about the security of your traffic within a data center if you're not using VPC. So you really don't want these API keys to be compromised and then have the lifetime extend infinitely. Some services, as I mentioned, may be outside the firewall. This was the builder case for one of our customers earlier. And like I said, if one of these things gets compromised, there's an unbounded amount of access when the secret is leaked. I mentioned that we considered just using client certs in between all of your services. Who's using SSL client certs in between your services? What are the good parts about them? You can revoke them. Yeah, if you have the revocation policy well defined. What are the bad parts about them? Yeah, generating them, managing them. You have your whole PKI infrastructure for your organization that's probably already in place, and integrating with that can be a pain. So we really like the idea of using SSL client certs. Like I mentioned, we're already using them between Claire and QUAY for a QUAY.io hosted solution. But when we talk about deploying this thing in the enterprise and deploying it behind people's firewalls, we're essentially asking them for either a whole slew of certs to be generated on our behalf, or we're asking them for a private key for an intermediate cert that will allow us to just generate certs that play nicely with their whole PKI. And if you've ever worked with like a large enterprise, you'd realize that this is usually a non-starter. So there's also some of our clients are also using load balancers that are managed by their ops team. So if you're terminating SSL at your load balancer, usually those load balancers have the ability to do client cert verification. But sometimes it can be difficult to get your ops team to even agree to it, right? To be like, yeah, we'll turn on client cert verification for this random third-party piece of software that you bought. How about next quarter? So this doesn't really meet the idea of having painless auth that was part of our original goal. So the thing that we settled on was HMAC. Does anybody know what HMAC stands for? I'm sure somebody does. Okay, well, HMAC is hash-based message authentication codes. So you basically just take your message. In this case, the message is an HTTP request, and you hash it together with a secret. I'd like to note that this is not actually how you generate an HMAC for any of the existing HMAC solutions. So please don't go back, implement this code, and then come and tell me that like my HMACs were wrong. But anyway, the idea is that you by hashing a secret together with information about the request itself, you get this very strong protection about being able to verify that the message that I've received hasn't been tampered with. I'd like to point out that the headers in the request body are also in there. This is both a good thing in that the request body can't be tampered with, but also a challenge, as I'll get to in just a second. Right, so some of the virtues, some of the reasons that we were attracted to HMAC are that you don't actually have to put your secret in the request like you would if you were using an API key. Additionally, because you're hashing the secret along with the request, this is just a simple, like, cryptographically secure hash, and it's a super fast algorithm. And as I mentioned, the request itself is signed, which means that if you're behind your firewall and if you're on a network that you trust, these things, the request is still signed, so you know that they're not being tampered with by that black hat that got behind your firewall. So this was, how many of you guys are using AWS? Who's familiar with the AWS v4 signing scheme? So it's essentially this, right? So there's a lot of prior art in using an HMAC to secure an API call. Amazon has been using them for over a decade to secure the EC2 and S3 APIs. And the way they invented these, or one of the really cool properties of not transmitting the secret is that you can actually send these things in the clear. And then the v4 scheme that we actually went out to implement has integrated a lot of the learnings from the v1 and v2 Amazon schemes that they started with. So here's a simple block diagram of what we set out to implement. And maybe don't photograph this because this isn't where we ended, but we essentially had HMAC proxies, right? So we built both a forward and a reverse proxy. And this was the idea of being able to layer security on in a non-invasive fashion. We had a secret store where an admin would go and generate a secret. This is similar to the IAM console in AWS, if you're used to that. So you'd go there and you'd generate a secret and you'd distribute that secret to all of your services. And then they would be able to generate HMAC at the proxy layer and send those authorized requests back and forth and verify the HMACs on the receiving side. So service A and service B actually know nothing about the authentication that's happening between the services. So we really like this idea. We went out and we built a prototype. We spent maybe a week or two building out the prototype. It was no more than one of our sprints. And we realized that this thing just isn't going to work at all. We were seeing 100% signature error rate. It seemed to be architecture dependent and not request dependent. So we had to take a step back and say, like, what the hell is going on here? And do we need to just like get rid of this whole project and start over? So hopefully we don't have to do that. So we need to answer, like, how did we end up here and how do we move forward? So as I mentioned earlier, the request is signed. Who thinks they know why HMACs failed, given that proxy architecture and given that the HMAC is signed? Why do you think it failed? The headers? Yes. So it's actually the request and the headers that get signed. Here's an example of an AWS v4 signature. I broke it apart to make it easier to see and obviously omitted a bunch of the data. But as you can see, it actually signs headers. And the set of headers that you're signing turns out to be super important. So our first idea was to just sign and verify all of the headers, right? Like, that's obviously the most secure. It's great. But it was quickly apparent that we ended up with extra headers. And where the hell are these extra headers coming from? So if our load balancer is there, right? Any kind of reverse proxy is going to add these headers on for you very helpfully and quite necessarily by default. But are these things required to be signed or not on the receiving side, right? So you're like, oh, that's easy. They all started with X forwarded. We'll just whitelist any header that says X forwarded. Easy peasy. We've solved the problem. Unfortunately, there are also things that will remove headers quite helpfully for you. So if you're using Nginx to do your load balancing, or if you're using Nginx as a reverse proxy, if you turn on the proxy caching module, it'll just go through and it'll strip off all of the cache-related headers. And I say helpfully quite tongue-in-cheek because this causes quite a bit of trouble if you've signed those headers and you need the values of those headers to verify that signature. Right, so obviously, the way you verify an HMAC is you take all of the same data that went to generate the original HMAC and you walk through that signing process again to recreate it. And if we've lost the headers, we can't actually verify the signature anymore. Okay, so what if we only sign the absolute minimum number of headers that we have to? Maybe just like the host. The problem with this is that some headers actually have really strong semantic meaning. So, cookies, yeah. That's a good one. Here's a header that's used for optimistic concurrency. So this header basically says only mutate the backend if the resource that I'm trying to modify hasn't been changed since yesterday. And so what if a black hat goes and strips this header, right? What if they say like, I'm just going to take that header because it's not signed and I'm going to remove it from your request. So now this means that my request is always going to mutate the backend. And this is definitely not what I intended when I originally created the request. This made me unhappy. So obviously the solution is to just sign the relevant headers, right? Which headers matter? It turns out in a proxy architecture you just don't know. So this was just kind of a non-starter. Since Amazon is generating these clients and Amazon is verifying the requests on their own side, they actually know which headers are semantically relevant. And this is actually done not in a proxy layer, but in a client library layer. So this is why Amazon can get away with it and why we couldn't. So we're back to our original solution. Let's just throw the whole thing away and we'll go get a hamburger and just decide where to go next. But we thought maybe there's just one thing we could do that would save our bacon, right? Maybe we could replace the authentication scheme, the signing scheme, with something else that works a little bit better for our use case. So JWTs are all the new hotness. Everyone's using them, so why not us? So this is essentially what a JWT is. It's a combination of a set of headers. The headers tell you how this thing has been encoded, right? So this JWT was signed with the RSA 256 algorithm, which takes a hash of the message and then signs it. There's some claims. There's a claims section to the JWT. In this JWT, we're claiming that the issuer of this token was the QUAY service, and we've also included a nonce. A nonce is a value that you don't use more than once. It protects you from replays. And then in the claims section, you're essentially answering like the what, who, the why, and the where of what this thing is claiming. And then the signature itself proves that the person who said they signed it is actually the one who signed it. So because we're using RSA, we actually have a really strong cryptographic proof that the person who holds the private key is the one who signed this JWT. So like we identified the virtues that we were going for with HMAC, we also identified a set of virtues for JWTs. So like in HMAC, a JWT doesn't actually transmit the secret in the message. So this is great if you have to send this thing over non-encrypted traffic at any point in your infrastructure. Because we're using RSA signatures, the secret is actually never transmitted, which means that we don't even have that bootstrapping process where we generate a pre-shared key and send it to all of the hosts. We can actually use the fact that it's asymmetric crypto to keep the private key with the actual person who's doing the signing. Right, so the JWTs are signed, which means that they can't be tampered with. They're resistant to replay attacks because we include a nonce with our JWTs. They can be transmitted in the clear because they're, it's just a signature. We're not actually transmitting anything sensitive. And we can also put information about the request itself in the claims section. So I'd like to say that, or I'd like to point out that we're not actually doing this, but it is an option if you have to have a stronger guarantee about the request itself. Because the responses aren't signed, we still actually recommend that you try and use a really secure network, or you use SSL everywhere where these things are being transmitted. So they have weaker guarantees about the request and the response themselves. And so this is our new architecture, where we've replaced the HMAC proxy with a JWT proxy. The parts in white are new. So we've replaced, basically, like I said, we just did a substitution, string substitution. Everywhere we used HMAC, we now use JWT. And you'll notice that instead of being a secret store, now the thing on top is actually a public key store. And this is actually, makes it easier to bootstrap a cluster. So now I'm going to switch and do a quick demo, hopefully, if this thing cooperates. Can you guys see that? All right, and then oh no. Okay, so what I'm going to do is I'm just going to spin up a service that we want to protect. In this case, I'm just going to spin up request bin. Request bin is open source, which I think is super cool. I never knew that. So here I have just my own local version of request bin. And I'm just going to create a new bin. Come on. All right, well, this isn't going to work so well on this resolution. Still there? Awesome. Okay, so here's my request bin. If you're familiar with request bin, it's just something that you can throw requests at and it'll do a thing. So in this case, I just used curl to make a request, and then it tells me exactly what happened as part of that request. So now I'm going to spin up all the stuff that I need to protect this using JWT proxy. First, I'm going to spin up QUAY, which is what we're using as our secret store, or our public key store. Everything's running locally on my laptop, but it would be the same in production. Then I'm going to start up, first I'll start up a reverse proxy to protect the service. So now I've got a reverse proxy that is running on port 8081 that I can send my request to, that I'm trying to send to request bin. Oh no. Right, so it's saying that I can't actually make that request because there was no JWT included in the request. So it's now protected by this reverse proxy. And now I'll spin up the forward proxy portion, which just uses the HTTP proxy protocol. So every client has every client has built-in support for it. So what you'll see is that it actually just generated an RSA public-private key pair on the local host, and now it's waiting for an administrator to go and approve that key. So this is what I mean about not ever actually having to transmit that key. That key lives with this forward proxy and is never actually transmitted. So now if I go over here, I'll see that there should be a new key request. So here's the new key request, and by approving it, I'm saying that you should trust this key represents that service. Right, so now our key is approved, so now we can mint JWTs. So if we go back and we tell our curl to use that proxy, which is running on 8080, we've actually successfully put a JWT onto our request on the way out and then verified it on the receiving side. And so what that looks like in our request bin is here. We've added a bearer token that contains the JWT, and this thing makes a lot of strong claims about the request that came out. And so we'll use JWT.io to just take a look at that. So here we can see that it was an RS-256 signed JWT. We've used all of the strong JWT claims that you need to use, like don't use this thing if it's before this time, don't use this thing if it's after this time. The issuer was this sample sender, so you can be sure that the request came from this person. And And then this is just the nonce to protect it from replay attacks. So this JWT can't be used again on the same verifier. Okay, so back to my slides. Okay, so as I pointed out, we're using RSA for this, which is really interesting because we have strong claims about who, or we have a strong idea about who actually signed this thing because that private key never gets transmitted. It's like the private key that you generate for your SSL certs. You're the only one who ever has access to that, so nobody else can claim to be you. It also allows us to, using a clever implementation of the key server, we can actually rotate our keys automatically. So this is pretty similar to the Acme protocol used by Let's Encrypt. So we can actually rotate our keys by just publishing a new key and signing that with our old key. So we can mitigate the lifetime of a compromised key. But unfortunately, generating an RSA signature is actually kind of slow. So I ran a test, and it takes approximately 9 milliseconds to generate an RSA signature on an M3 medium instance on EC2. And when we're talking about service-to-service auth, this is actually kind of a long time. And this is an area that we're looking to improve, the JWT proxy. Which brings me to our future work. Where do we see this thing going? So obviously, we want to do performance improvements. So RSA is only one of the required, or is only one of the available signing mechanisms for a JWT. You can also use an HMAC with a secret. And because we know the public key of the person who is sending these original requests, we can actually encrypt a secret and send it back with our response. This may sound really familiar because this is exactly how SSL works. We could actually do that within our sessions for our JWTs. And that would get us approximately 1,000 times speed up on generating those signatures for that session. We can also integrate with your cloud providers to do automatic key approval. You saw that step where I had to go and approve the key manually. But if you're using something like Kubernetes to schedule your microservices, Kubernetes already knows what you're running and where. So Kubernetes could say, like, automatically approve keys that come from this place at this time because I know I just started a service over there. And this would really improve the bootstrapping process for bringing up a new cluster with this service-to-service auth. We also want to make the key server responses cacheable. So right now they are cacheable, but they're not signed. So we want to also include a JWT with the key server responses. So this way the key server doesn't become a critical part of the infrastructure, like a tier 0 dependency. So if the key server goes down, as long as you have a previously signed key server response, you should be able to continue operating in the steady state. And we'd also like to make improvements to the way we handle nonces. So if any of you guys have ever heard of server-side nonces, you can actually generate a nonce on the server side and say, use this nonce the next time you make a request. And in this way, you can actually issue sequential nonces, and you can really get a much higher amount of efficiency when storing those nonces on the verifier side. Because right now, we have to store what's essentially a random value for the entire lifetime of that JWT, which is an attack service, is a denial of service attack surface. If you can mint valid JWTs, you could mint millions of them and just exhaust the nonce storage. As Brandon mentioned, this is open source as of a couple weeks ago. You can find it at github.com CoreOS JWT proxy. We encourage contributions. We've been running it in QUAY hosted for a couple weeks now. It works really well for us. And with the QUAY Enterprise v1.16 release that went out last Friday, we're also now bundling this with QUAY Enterprise for securing Claire and those other services that I mentioned before. That's all I had. Any questions? In the back? So the question is, do we have plans to integrate with Kubernetes? Yeah, so that's where I was talking about automatically approving keys based on integrations with the infrastructure provider or the cluster scheduler. Because like I said, that thing knows when it spins up a new service, so it can approve those keys automatically. And you can make the bootstrapping a lot better than having to manually go and approve keys. We also have support for pre-shared keys in the JWT proxy. If you have these things in like an auto-scaling group, you definitely don't want to have to go and like click approve every time your instance set changes. But pre-shared keys are, I mean, ideally I'd like to integrate with Kubernetes and then make it easier to bootstrap the cluster rather than have to use pre-shared keys.
How do you establish initial trust with the public key server?
You're saying, how do you know to trust the public key server?
If I compromise that, then I can...
So the public, right, so the key server only stores public keys, right, which is already freely available information. If the question is, how do you make sure that the public key server is not telling you to use public keys that are not officially approved, right? So we're relying on SSL in the key server right now for that. This is actually a weak point because SSL relies on all of the CAs that are trusted by your OS itself. So we're also considering, like I said, including a JWT with the response from the key server, and that would be something that we just issue a private key for those responses that expires on the order of years. So it would be something, it would be like a single bootstrap where you'd have to say like, trust key server responses that are signed with this key. But again, it is a bootstrapping process. Another way would be to use a self-generated CA, like your own CA, and then only trust that on the machine that talks to the key server. So that way you don't have to worry about someone compromising one of the other million CAs that are in every machine now.
Have you considered making this into a library so people can integrate it in their services directly instead of using the proxy?
So the question was, have we considered making it a library that people could integrate? So it is actually built as a library in Go, and we just provide a like main.go that you can use. So you could actually just take out the parts that generate the signatures and apply them and use them as a library. We really wanted to make it, we really wanted to go for that non-invasive approach. So like Claire being an open source project, we didn't want to have a bunch of like QUAY auth stuff in Claire. So you could choose to use it as a library. It is built as such. But like I mentioned earlier, you'd lose the language independence then. So you'd have to use all of your stuff in Go.
It seems that authentication authorization are a little bit separate now. Why not go the auth way that also nicely integrated? For example, we use auth with JWT and JWK so that the JWT actually contains also the scopes that this request is authorized for.
Right, so that's like the, yeah. So the question was, why don't we use the OAuth, basically OpenID Connect version, right? Where the,
OpenID Connect is even more well-defined than auth 2.
right, so OAuth 2, the tokens are usually actually opaque. So if you think of like a OAuth token that you get from Google or from Facebook or whatever, those things usually aren't actually signed, and they have the same compromise problem of just using like an API key. But what I was mentioning is that in OpenID Connect, the OAuth token is actually a JWT that is also signed. And that actually works really well, but again, because it doesn't have like the nonce support, if that thing is compromised, then you could use that to replay requests over and over and over again. So if we're protecting the money service, we really don't want, like, even if I have the scope of being able to deduct money, I don't want somebody to be able to compromise that key and then deduct money over and over and over and over again.
Can you use such HSM or other VPN features to generate key?
So the question was, can we integrate HSM with the key generation?
If you can generate the private key with HSM, with some HSM in the server.
So the question was, can we generate the private key with an HSM in the server? We haven't actually implemented that, but that's super cool, right? So we have Matthew Garrett on the CoreOS team who's working to basically turn the TPMs into an API. And by integrating with that, by integrating with all of his code, we could do that, and that would be really cool. It would be really nice to know ahead of time that this server already has a key also, right? So you can skip the whole bootstrapping process if you get from your server manufacturer, like this thing already knows about this, like this thing already has a key. You don't even have to generate and approve it. You can just jam all of those things into your trusted keys store. So yeah, that would be really cool and super secure. I think Matthew's actually giving a talk about the trusted compute stuff that we're doing later today. So I encourage you to check that out too. Okay. Anything else? All right, thanks guys. Sorry about my voice.